Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 4th, 2026, just 2 days ago. It introduces a new metric called the Balanced Information Score, showing that models can reach full data performance using only 10% of the training set. The paper is titled Training Data Efficiency in Multimodal Process Reward Models. And, as we'll see later, the potential for massive compute savings is really exciting. And for those interested in the implementation, the authors have shared their code on GitHub. So, Figure 1 illustrates exactly where those savings come from by plotting the model's micro F1 score against the number of training steps. The solid orange line tracks the performance of a model trained on just 10% of the data, selected using their new method. Crucially, notice the orange star. It marks the point where this small subset matches the final performance of the full dataset, which is shown by the black star way over to the right. This represents a reduction of 95.5% in training updates, proving that smart data selection can effectively replace brute force scale. Well, Table 1 details the statistics for these different training subsets. Comparing the full data and random 25% columns, we see they are statistically almost identical, with very similar error step ratios and average MC scores. This suggests random subsampling preserves the general data distribution without filtering for difficulty. On the other hand, the low MC and mixed columns on the right show significantly higher error rates and lower scores, which hints that these selection methods prioritize more challenging or complex reasoning steps. Alright, Figure 2 visualizes the performance implications of this redundancy. In the first panel, Figure 2a, the micro F1 score rises steeply and then plateaus, meaning that simply adding more random data yields diminishing returns. Moving to the third panel, Figure 2c tests if we can do better than random selection. Here, the red curve for the mixed 25% subset clearly beats the orange random baseline, demonstrating that prioritizing rollouts with mixed positive and negative signals is far more effective. So, while Figure 2 plotted the trends, Table 2 lists the exact performance metrics across two different backbones, intern versus L on the left and QN on the right. Focusing on the intern versus L model, look at the 10% subset section. Here, the BIS selected data achieves an overall score of 65.46, which actually slightly outperforms the full dataset result of 65.12. The gap is even more dramatic for the QN model on the right. At just 5% data usage, random selection drops the score to roughly 53.5, whereas the BIS method maintains a score of 64.42. Well, Figure 3 reveals the logic behind this selection by breaking down its two components. In the left chart, which tracks reliability, notice that the black coverage curve peaks in the middle range rather than at the top. This indicates the method filters out noisy data, but also ignores trivial, high-reliability cases that offer little new information. By comparison, the right chart for the mixture term shows a steady upward trend. Here, the coverage rises toward the maximum value, confirming that the score prioritizes examples with high variance to maximize the information gain per step. Alright, since Figure 3 explained the theory, Table 4 now validates it by ablating those specific components under a fixed 25% budget. The top row shows the full BIS method, which achieves the highest overall score of 65.46. In comparison, the sections below reveal that using only the mixture or reliability signals consistently degrades performance, with the reliable-only subset dropping the overall metric by over 2 points. This confirms that the efficiency gains come specifically from the intersection of these two factors. Wrapping up, two takeaways stand out. First, data redundancy is a massive bottleneck in reward modeling, and second, we can bypass it completely with smart selection. By focusing on mixed but reliable examples, researchers can slash compute costs by over 90% without sacrificing performance. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.